Discussing about the remarks on the methods that we have so far devised. So, exact equations, you know how to solve it. So, you cannot solve all the equations by these methods only. So, you have to verify whether it belongs to whether certain method works to that equation or not. Only if you make sure that it can be the method will work for such an equation. So, there are some conditions you are verifying so that you can attack such a method to solve the problem. Exact equations, for example, you just have to check dou m by dou x, okay. Dou m by dou x, dou m by dou y equal to dou n by dou x, that condition of exactness you have to verify. And if it is not same, you have to verify certain forms that I have given for different v of x y values, v of x y function. If it is x, v of x y is x, v of x y is y, v of x y is some special form like x minus y, x by y, or x y. In that case, you have a certain form to verify. If it is that, whatever that you verifying expression, it should be function of that v, that specific form of v, specific function of that form of v. Then you know how to get the integrating factor. By multiplying the integrating factor, you can integrate the equation and get the general solution of the equation. This is how, if you are given an equation, you just have to see what method you can apply, just by looking at the equation. Sometimes smartly by rearranging you can directly integrate, okay. So, these are the methods, standard methods that are available to solve the first order ordinary differential equations. Forms second order. So, let us move on to second order ODEs. Second order ODEs, how do I solve it? So, y double dash again. So, what is the general form? F of y double dash y dash y comma x equal to 0. So, this is the general form where f can be anything. So, in an explicit form, in an implicit form. In an explicit form, you can also have an explicit form, that is you solve for the higher derivatives y double dash, which is equal to some small f, which is also arbitrary function f, which is, let me write like this, x comma y dash. This is also general solution, where general equation of second order, because highest derivative is second derivative, and you have this. So, these equations, if it is a general f, you do not know, you may not be able to solve. So, you have to go for, so there is a question of existence of the solution itself. In the domain it is defined. The domain actually x is the independent variable. So, that is only the domain is R. Y is the dependent variable, y takes the values, real values, y dash and y double dash also takes the real values. So, that is the solution. So, not all equations can be explicitly solvable, certain forms of equations, some ad hoc methods we have to solve the second order equations. I will give you one or two, okay. So, in standard forms, one simplest second order or higher order for that matter. So, if I have y double dash equal to only function of x, I do not have y and y dash terms. I know simple integration. So, y dash equal to integral x naught to x f of x dx plus y dash at x naught. I do one more integration from both sides, okay. This is by integrating from x to x naught. This is what it will give you. One more time if you do, you get y at x equal to x naught to x. Now, if I use this whole thing, whatever I have here is a function of t, so x of t f of s ds is function of t dt, plus you are integrating from x naught to x naught. So, x naught minus x naught y dash at x naught, because it is a constant, you are integrating from x naught to x, and you have here y at x naught minus y at x naught. So, y at x minus y at x naught. So, that I bring it here. So, you have y at x naught. So, this is arbitrary constant, this is because this y is unknown function, y dash is also an arbitrary constant. You have, if you call it C1 and C2, so this is your general solution. I have a solution y, that has one arbitrary constant C1, another arbitrary constant C2, which is given like this. Okay. So, these are any order for that matter. So, one n derivative is equal to, if I have function of x, n integrations gives me the general solution. Okay. So, this is a trivial form of f, for which if it is function of x, I can simply integrate many times and get the solution. Okay. So, what is the different form, another form that you can work out? So, if I have y double dash equal to f of x y dash, there is no y, the right hand side function that does not involve the terms of y, I have only y double dash and y dash. In this case, let me choose, let y dash equal to some variable z. Okay. dy by dx equal to z, z is a function of x. Okay. So, I replace this dependent variable y dash as new dependent variable z. So, then dz by dx is y double dash. So, left hand side I can write dz by dx, right hand side I can write fx z. So, this is the first order ordinary differential equation. If I know how to solve this, then I can find my z, and then I go back and do one more ODE, y dash equal to z. Having known z from this ODE, I put it here and I solve this second ODE to get my y. That is the general solution of, that is how you solve the second order equation. So, you have somehow found to solve the second order equation by solving two first order equations, okay, simultaneously. So, this gives me a feeling. So, if you, so I can convert this into a system that is possible, is equivalent to this second order equation. We can actually write, you write it as y1 as y, y2 equal to y dash. Okay. I am trying to put this as a vector form. So, you try to write this, you try to make a vector with y and y dash. Okay. Then what happens to d dx of this vector y1 and y2, which is equal to, in vector if you differentiate each component, you can differentiate, this is equal to dy by dx and dy dash by dx. Okay. dy1 by dx, that is dy by dx, dy2 by dx, that is equal to d dx of y double dash, that is actually d square y by dx square. So, this is dy by dx is nothing but y2. So, this is my y2, and this is equal to d square y by dx square is f of x comma y dash, that is y2. Okay. So, you can see this implies, you can see d dx of some z, it is a vector form, is equal to, this whole thing is like a some function, let us call this some g of z bar, where z bar is y1 and y2. So, you can convert second order equation into a first order system of equations. Okay. So, like that you can convert any nth order equation into an equivalent first order system of equations, or first order equation for the vector n by 1 vector. Okay. It is like this, these are n rows and 1 column, n rows and 1 column. Why we have seen this? Because you in the solution method, what you have is this equation. When you put this in this special form, when I write y dash equal to z, and what you have is two ODEs, if you simultaneously you solve them simultaneously, this equation and this equation, that is how you get the solution of this. That means these are your simultaneous equations. If you solve it, that is equivalent to solving the second order equation. Okay. So we are not interested in that way, because you do not know how to solve the system of equations, simultaneous equations, because these simultaneous equations here, they are easier to solve. So that is why we are the basic idea is there. So the second order equation we are reduced into two simultaneous equations, first order, which can be solved. Okay. In this special form you can do that. If I have y, that may not be possible. Okay. So I will give you an example. You try to solve y double dash equal to square root of 1 plus y dash square. I do not have y, I have y dash. So let y dash equal to z, then your dz by dx, which is equal to square root of 1 plus z square. Now I know how to solve this. Okay. Then I can solve this. First let me solve this. This implies dz by square root of 1 plus z square equal to dx. I can integrate both sides and write the arbitrary constant. So this implies this is actually sine hyperbolic inverse of z equal to x plus c. This implies z equal to sine hyperbolic x plus c. Okay. So now having known your z, you come back and put it here, y dash equal to sine hyperbolic x plus c. Let me call this C1, so that you have one arbitrary constant is C1. So now I am trying to solve this equation, I am trying to solve the second equation. Okay. This first equation by replacing z, having got the z from the second equation as a general solution, that I bring it here and put it. So now I can integrate directly. This equation is simply this is dy by dx equal to sine hyperbolic x plus c. So you can write dy equal to sine hyperbolic x plus c1 into dx. The variables are separated, so you can integrate both sides plus c2 arbitrary constant. So this will give me y equal to cos hyperbolic x plus c1 plus c2. So this is your general solution of the second order equation, this with two arbitrary constants. You can easily see two arbitrary constants, c1 and c2. If it is a second order, you will have two arbitrary constants. Okay. So it is called general solution because it involves two arbitrary constants. A solution involves two arbitrary constants, c1 and c2. So if the equivalent system is equivalently second order equation, if you equivalently write it as a first order equation for the vector like here. So what is the general solution? General solution, you will get z of x as some form of let us say some known function. Once you solve this, some g of z bar comma, what is the constant here? Constant means the solution z bar at certain point. Z bar is a vector. Z bar is a vector. Z bar at certain point is y1 at 0, y2 at 0. Let us say these are y2, that is z at 0. That is simply a vector. So you have a vector as a constant. So this is how you get the general solution of that. So you have two arbitrary constants c1 and c2 in the second order equation. In the equivalent case also you have one arbitrary constant c, but that is a vector. Okay. So the vector is having two elements, so 2 by 1 vector, so you have two arbitrary constants there. So they are actually equivalent. Okay. So this is the general solution for first order vector equation. This is the general solution of the second order equation, scalar equation with two arbitrary constants c1 and c2. Okay. So with this, if you have in this special form, you can solve it, you can solve the second order equations. This is an example. Let me give you one more type where you can solve. So third form I will give you so that you can solve. So y double dash, if I have f, y and y dash, if I have like this, can I solve this second order equation? So, again as usual, if I choose let z equal to y dash, then z dash equal to, that means dz by dx equal to f of y and z. Okay. And you see, I have both x variable and y is there here. So, I cannot hope to solve this, but I can solve it if I presume that what happens, you look at this one, since dz by dx, I can write it like dz by dy into dy by dx, but dy by dx is z. So, z into dz by dy, since this is dz by dx equal to z into dz by dy, if z is a function of y, if I can assume, that means I have y dash that is function of x, as a function of x which is z, if y dash, that means you have a solution yx whose derivative y dash of x, this is equal to, this is also function of x, right, y dash is dy by dx, y is, so this is a function of y of x, if you can write some function of y of x. If the derivative is function of y of x, then I can that means I can see that y dash is function of y, that means z is a function of y. If z is a function of y, dz by dy makes sense. Okay. So, that I can replace dz by dx here into z into dz by dy. Z is now depending on y, okay, because y, z is actually y dash, that is actually function of y. Okay. Such a thing, if it exists, you have a solution yx whose derivative is actually function of y of x. If such a thing exists as a solution, you assume that it exists, okay, then I can write like this. So, that I can replace dz by dx is this equal to f of yz. Now, it is, I could remove x variable in the domain. So, I have dz by dy f of yz. So, this is a first order ODE for the dependent variable z with an independent variable y. So, if I can solve this, I can get my z, again you go back and from this you can solve for y. Okay. So, this also I give you one example and then I will. So, solve y double dash equal to y power 1 by 3, one simple example. Okay. So, I have y here, it's clear simple example. So, you can replace z by y double dash dz by dx, let z equal to y dash, then dz by dx equal to y double dash which is equal to y power 1 by 3. Clearly dz by dx is function of y. So, I can write dz by dx equal to z into dz by dy equal to y power minus 1 by 3. So, this will solve dz by, so z dz I can integrate directly. So, y power 1 by 3 dy. So, how do I integrate? So, this will give me z square by 2 equal to y power 2 by 3 by 3 by 2 plus arbitrary constant. So, this is my general solution. So, from this I can get my z of y which is equal to 3 y power 2 by 3 plus 2c, okay, plus or minus square root of this. This is my z. Okay. Z square is this. So, you have z is plus or minus square root of this. This is equal to dy by dx because y dash is z. So, now I can solve dy by 3 y power 2 by 3 plus 2c under root equal to plus or minus dx. This is what is the first equation becomes. So, this you can solve it by integrating. Okay. So, you can integrate this easily. How do I integrate? So, you can integrate plus some other constant C2. You call this C1, 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 then it will become C2. So, how do I integrate this? You can integrate by taking t power y power 2 by 3 plus 2 C1 as some t. This will give me 2 by 3. So, 2 y power 2 by 3 minus 1 is minus 1 by 3, okay, dy by dx dy equal to dt. Okay. So, this will give me this integral as I can write dy as dt by 2 times y power 1 by 3. So, from this you can get your y power 2 by 3 equal to t minus 2 C1 by 3. Okay. So, this square will give me 1 by 3. Y power 1 by 3 into root t. So, now I have to replace 1 by y power minus 3 as so this is equal to plus or minus x plus C2. So, this will give me this I have to rewrite. So, 1 by 2 out, y power 1 by 3 is 1 by 3 t minus 2 C1 square 3 square divided by 2 into root t dt equal to plus or minus x plus c. Now, this is simply function of is a polynomial divided by. So, this you can easily integrate and get the solution. Okay. How do we do this really? So, this implies 1 by 4 36. So, there is no only one t. So, 1 by 18. Okay. So, integral t square minus 2 t C1 plus C1 square by root t dt equal to plus or minus x plus c. So, this will give me 1 by 18 t square 2 minus half minus 3 by 2 minus 2 root t into C1 plus C1 square t power minus half dt equal to plus or minus x plus c. So, finally, you get t power 3 by 2 minus 3 by 2 plus 1 is minus 1 half. Okay. So, minus 2. So, 1 by 9 minus 1 by 9 t power half t power 3 by 2 into 2 by 3 27. Okay. Plus 1 by 18 C1 square t power under root into 2. So, 9. Okay, equal to plus or minus x plus c. So, this is, so you have c and C1 are arbitrary constants. So, that will solve the problem. Okay. So, this is your general solution, where t is, you replace t as 2 y power 2 by 3 plus 2 C1. Okay. So, you have functions of, in terms of functions of y and x as a general solution for your second order ordinary differential equation. Okay. It is given as this. So, these are the ad hoc methods. If it's your right hand side is in certain form, only in the specific form you can solve it, otherwise you do not know how to solve it. Okay. All the, like in the first order ordinary differential equations. Second order linear ordinary differential equations can be solved. Okay, so linear second order ODE will solve it. So we'll go to linear. So far any form, now it's only linear. Okay, so what is the form? So once you say linear, it should have only y dash, because the second order you should have only y dash and y double dash. Okay, let me put it y dash here, y here. So like this I should have only these terms. Okay, and their combination I should have, which should be equal to some function of x. Okay, so whenever you have a dependent variable fx, so let me write this, fx is the right hand side. Whenever I have a certain form, if it's linear, I should have only y and y dash, y double dash, not its squares, not its powers. Okay, so what is how you can fill it up? So only its combination. So sum or addition. So I will just multiply some a0 of x, a1 of x, a2 of x equal to fx. So this is the form you have. This is the second order linear ordinary differential equation, where f and a2, a1, a0, a1, a2 and fx are given functions. Okay, functions of x only. And the moment you write this, higher order derivative, the coefficient is a0 of x, that should not be 0. So that means your domain should have values, all values of x, where a0 of x should not be 0. Okay, so that means you cannot have a domain at which you have a0 of x is 0. Okay. So how do we solve this equation? So this is the linear second order ODE. Before we solve these equations, we will try to convert this into system of equations. Okay, so like I just explained earlier, here also you can convert this equivalent first order system of equations, that is y1 y2 as a derivative equal to, what do you have? So what is your y1? y1 is y, y2 is y dash. Okay, so you have dy1 by dx, which is dy by dx, that is y dash, which is equal to y2. So I have y2 is the first ordinate, first equation, dy1 by dx is y2. What is your y2 dash? ddx of y2 is ddx of y2, which is y double dash. Y double dash I can get it from the equation, that is fx by a0 of x minus a1 by a1x by a0 of x. What is y dash? Y dash is y2, that is y2 minus a2x by a0 of x into y. What is y? Y is y1, so I have y1. Okay, so this is the system of equations. So you have two equations, two coupled equations in y1 and y2. So this is actually equivalent to ddx of y1 and y2. You can split it in as a matrix times y1 and y2 plus some vector, which is 0 fx by a0 of x. Here if I multiply something, so that I should get my y2. So I should have 0 1, and here minus a2 by a0 minus a1 by a0. You multiply it, so that second after multiplying this into this is what you get, plus if you add this part which is known, so this is the right hand side. Okay, so you have something like equivalent to some x dash, x is a vector which is y1 and y2, equal to some matrix A which is depending on x, because A naught, A1, A2 are functions of x, into x again matrix, it is a vector. So, this is your linear system. The right hand side is actually some B is a vector, okay. This is a vector, this is a vector, where B is 0 and f by A naught, which is also function of x, okay. So, this is how you can convert any second order equation into a first order system. This is called system. You do not know how to solve this system of equations, but what we do is we in the course we will try to give you methods to solve this second order equation, and same way you can try to pose this any higher order equations, okay. This is the second order. Higher order equation you will have, instead of a second derivative you will have nth derivative. So, you have nth order differential equation in the same way, in the same light you can give nth order differential equation, ordinary differential equation which is linear and its equivalent system. So, in this way we can define nth order linear ordinary differential equation by the same way. So, you can have, instead of y double dash you have nth order derivative, you have next term is n minus 1th derivative, and then up to 0th derivative, that is y, and equal to right hand side f. All these dependent variables y, y dash up to yn derivatives should be linear, and their coefficient should be some function of x, and then you can combine them with addition which is equal to fx. That is the most general form of nth order differential equation that can also be solved by the methods you devise for the second order equation in the same way. The more is just same, you just follow the methods of second order, you can apply for this higher order, small change will be there, okay. So, the nth order differential equation, higher order differential equation, you can also write equivalently a system. Here second order you have got a x as where x is actually a vector y1 and y2. So, it is a 2 by 1 vector. So, if it is a nth order equation you will take y1, y2, yn. So, it is a n by 1 equation, you will go up to yn, y1 where y1 is y, yn is actually yn minus 1th derivative, n minus 1th derivative of y is your yn. Like that you can go on, you can make your x, and you will get a n by n matrix, x is n by, in that case it will be n by 1 vector, b is also n by 1 vector. So, like that you can make a system of coupled equations, n coupled equations, that you can represent as a system of first order equation for the vector n by 1 vector, n by 1 vector. So, we will try to give you elementary methods how to solve second order equations, and then you will try to generalize for nth order equations.